welcome everybody. Earlier we learned about single variable optimization, and that means that we need to adjust one parameter in our system to realize another. In the next coming days we will focus on the multivariable optimization, and that means we have a more complex system where we can adjust several parameters in an optimal way to realize a desired parameter. The teaching example that is most often used in Lean Six Sigma training for that purpose is a catapult, like the one I have here. This catapult can be used to shoot a ball, for example, over 2 meters of distance, and we can realize that with a fast moving ball with a high curve or a slower moving ball over a, for example, shallower curve. What we need to find out in the next coming days is what is the mathematics to find the optimal settings for a catapult like this to realize a desired parameter. This problem occurs a lot of times in a lot of factories and a lot of different technical systems. And we will use a catapult to try to get a grasp of that problem. We will not use a wooden catapult like this, but we will realize our own catapult today. So our goal of today is design and build a precision catapult which is able to shoot balls between 3 and 5 grams. So that is the products that we realized yesterday. Over a distance between 1 meter and 2.5 meters. The catapult is easily adjustable. We have at least 2 discrete and 1 continuous parameters. For our teaching example here, we have a discrete parameter like this, where the rubber band is fixed. Another one is where the cup is fixed. And we have here the continuous parameter, what is the angle at which the arm is pulled back. The catapult that we will build today uses as little material as possible. We need to divide all our materials over the teams evenly. The maximum size is 0.4 by 0.4 by 0.4 meters. And the best catapult today is the one that achieves the best precision. Okay? So when we want to realize a construction like this, we first need to think about the degrees of freedom. So we want to move the ball along a desired trajectory, and that means that we fix its degrees of freedom. How many degrees of freedom we have? We can explain that by using just a simple box. So we have 3 translations for this box. 1 in this direction, 1 in this direction, and 1 in this direction. So that's 3 translations. And then we also have 3 rotations. 1, 2, and 3. So think about it. Every time that you mount something or fix something, you always have to think about these 6 degrees of freedom. For a car it looks like this. We have the transversal movement, acceleration and braking. We have steering. We have bumping up and down. And then we have the 3 rotations. First of all, jaw, pitch, and rolling. So for our catapult. We want to only use our creativity when we have found and stole the best ideas out there. So what we always do in problems like this is we start with the benchmarking, stealing other people's best ideas. So the first catapult that we can steal ideas from, I just showed you, the teaching example, and then we have bought 4 different types of catapults. And for your design, you can steal the best ideas of these catapults. So how do we want to analyze these catapults? Yeah, first we use our function model. So we make a function model of our catapult. What are the different functions? And then we look at how these functions are fulfilled with our benchmark products. And then we have an idea of what the best catapult could look like. Okay? So we make our function model and we start with the fixation of the ball. So fixation of the ball is rotation symmetrical. So we only need to fix the 3 translations. What you see here is the ball with, for example, a 3-point fixture. That could be the best solution. So the first function is fixation of the ball. The next is that we need to fix the trajectory of the ball over a line. And what we use in a catapult is an arm with a pivot point, a hinge. So that's our second function. Third function, when we have fixed the ball to move along a trajectory, then we need to apply force to accelerate it along that trajectory. And with a catapult, we use elastic potential energy to do it. That's our third function. Fourth function is we need to release the ball. And we do this by deceleration of the arm. Fourth function. Fifth function, we have a lot of energy now in our arm and we need to dampen that. Or else our catapult will destroy itself or it will deform and shoot every time in a different way. So we need to absorb our kinetic energy by some dampening material. That's the fifth function. We arrive at our last function, and that is that we need some framework to fix the position of the catapult. And we want to do it by not determine or fix our catapult, but we want to fix every degree of freedom exactly one time. I want you to think about a table on 4 legs. If not all legs are exactly the same length, it can still move. And a table on 3 legs, that's the stable solution. So that's not over-determined, but exactly right. And we want to have as little play as possible in our frame. So that's the 6th function. We now have a function model of 6 different functions. Here we have our overview, and now we can use this overview to analyze our benchmark products. We go in the back there from right to left, but we will start with the teaching example I showed you earlier, the wooden catapult. And the fixation of the ball position, it's a cup, and it's an easily adjustable cup on this arm. The trajectory of the ball is a hinge with 2 wooden holes. The wooden holes are quite close to each other, and we have a heavy wooden arm. The force used to accelerate the ball is a rubber band. Released ball is the heavy wooden arm is stopped by a metal pin. The kinetic energy is absorbed by, I can show you here, a plastic or a small rubber rectangle here. And the frame, we have a wooden base with our pivot point just above the table, very low. So we go to our next benchmark product. Yeah. First we look at the strong points, and the strong points in this design are obviously that it's very easily adjustable. With 2 discrete and 1 continuous parameter. Then we have the so-called X-bolt. You can see it here. You're able to read faster than I can talk, so you can look at how this catapult solves our functions. The strong point of this I want to draw your attention to is the alloy lightweight arm, and that's this. And you have to use something like that with the other materials that we have. If you would try to make a more heavy arm, you just destroy our materials. So please use the same type of lightweight arm as this X-bolt uses. Then we have the Da Vinci catapult. Again, you see all the solutions here, and I want to draw your attention to the strong points, and that is different than the two previous examples that we saw, is that the two hinge points have a bigger distance to each other. That means that the arm is much less able to rotate. And if the arm is much less able to rotate, then we're sure that the ball is not has not a lot of error sideways. It's a big strong point in the Da Vinci catapult. Another strong point, which we also want to draw your attention to, is that the arm is decelerated on a foam block, which has the same angle as the position of the arm. Then we have here another example. It's from a game called Catapult Wars, and the strong point here is a very simple wooden frame, and with a pivot point also above the table, which means that we can make nice steep curves, which is not possible with the very first catapult that I demonstrated to you, where the pivot point is very low on the table. Here you see the pivot points. The last example that I want to show you is an electrified catapult, throwing these kinds of balls for sporting practice. And the strong points are the 3-point support for the ball. So of all the examples, this one is the only one that does that 3-point support, and you can see it here. So the ball rests on 3 discrete points. Very smart. Next one is it uses ball bearings instead of just wood or metal or metal-wood contact. There's real ball bearings, and they're inside here. And the last one is this is the only catapult that uses metal springs instead of rubber bands, or in the Da Vinci case, the deformation of the wooden spring bars. Here you see the spring in the blue catapult. Okay, now we have looked at the solutions of the different benchmark products. We can bring them all together in our so-called morphological map. And that is what you see here. On the left side you see the different functions, and on the right side all the solutions that we have seen. And now we can draw in the solution that was chosen for the very first teaching example, called the Stuckerpult, and that looks like this. The next one is for the X-bolt, and one for the Da Vinci catapult, Catapult Wars, and the blue catapult. And what we can also do now is just think about, from our engineering judgment, which of all these solutions will give us most probably the best possible precision catapult. If we do that, we might arrive at these best solutions. So the fixation of the ball, easy to adjust with 3-point support. The fixed trajectory of the ball, an alloy lightweight arm, with 2 holes, 2 hinges far from each other, using ball bearings. How to apply the force? obviously not a rubber band, but a spring. Release of the ball, easy to adjust. The absorption of the kinetic energy of the arm, a foam block, the bigger the better, with a large contact surface. So fixation of the catapult, a simple base with a pivot point above the table. So that might be our wish list, like a Chinese menu for our best possible catapult. Some assembly guidelines. Please only drill holes and saw in the PVC material. That's the grey plastic material that we have. Don't drill or saw in the black POM materials that you will find. Don't draw your bolts into the aluminium profiles, as you can see in the picture. Use countersunk heads only with countersunk holes. Be economical with all materials, also the ruler stickers. And then I want to show you two design examples that you might find useful. First of all, how to attach the lightweight U-profiles that you will use for your catapult arms. You can attach them to the Bosch profiles as shown in the picture. So you just use two corner elements and 4 sets of nuts and bolts. Next example, how to fix how to use the roller bearings. What you see here is a Bosch profile, Allen screws, 3 sets, 2 shins, the ball bearing, and the POM strips, black POM strips that you can find, and 2 sets of sliding nuts. And then you can realize something like this. So the ball bearing is here. So what you fixate with this is 2 translations, this one and this one. And what you also fix is the translation in this direction, but not in that direction. So you might want to use the same thing as here on the other side to also fix that. Then you also fixated this rotation and this rotation, but not this. And that it might be exactly what you want to have your rotation of your arm. Okay, that's it. Have fun today, and at the end of the day we will have a contest which catapult of you is able to shoot with the best precision. So we will shoot like 10 balls and we will see what the catapult is for which those balls are as close together as possible. Have fun. Thank you very much.